Okay, problem 3.30, derive the transformation from position space wave function to the energy space wave function, Cn of t, using the techniques from example 3.9. Assume that the energy spectrum is discrete and that the potential is time independent. So we're just going to do the exact same thing that we did in example 3.9 to set this up, except now we're dealing with the energy states instead of position and momentum. So we're going to set this up the same as before, where I'm going to get my energy state by taking inner product of the energy eigenvalue or eigenfunction with the state vector. Like this, I'm going to expand my state vector in terms of projection of the projection operator in x, since I'm trying to get a conversion between n and x. So this is going to give me an inner product of n, the front, and then the same integral dx projection with x. This is obviously going to go to psi of x comma t, as we've known from before. If I move the integral over to the left, this is going to give me an integral, which is the inner product of n with x, and then psi of x comma t dx. And this term is the energy state. This is the energy state of my system in position space, which doesn't necessarily make that much sense. However, we can recognize that this term, the flipped version of this is the energy eigenstate in x space. Right? So in the same way that something like the inner product of x on the general state vector s of t, how at the beginning of the chapter we defined this as the wave state or the system state / system eigenstate in x space, right? In the same way that we defined that, this here is the energy eigenstate in x space. And we actually already know what the answer to this is, because we know that we have the time-independent Schrodinger equation, and way back in chapter 1, when we solved that, we found that there was this very nice eigenvalue equation, which is that h hat times the time-independent state is equal to the energy of the system times that same state, right? So in that case, this term right here, psi sub n, which is the time-dependent wave function, is in fact the energy eigenstate in x space, right? Because this is in terms of x, right? We always express psi n as a function of x, right? So in that case, if this thing is equal to psi n of x, then this is just the complex conjugate of that, right? Because I can rewrite this as the inner product of x and n and just flip it by adding a complex conjugate at the front and then psi of x comma t dx, in which case this is just equal to psi n star psi x comma t dx, in which case this is my final answer, right? And if I look back, this is the position space wave function, this is the energy space wave function, Cn of t. So this is equal to Cn of t, right? And we found it by using this sort of transformation. So once again, normally if you wanted to find something like Cn of t, that's not necessarily that easy to do, and you would have to do a very complicated proof to do it. If you didn't already know that you can use Fourier transforms to transform from one to the other, you would have to do the very complex proof. But here, you can just sort of plug and chug it into this equation, redefine your state vector in terms of projection operator of whatever basis you're trying to find your eigenfunction in. And just like that, you can sort of like slowly massage your way to a formula that ultimately is sort of the Fourier transform. Obviously, we already know that the Fourier transform is what allows us to transform from one basis to another. But if you didn't know that, then using Dirac notation would allow you to sort of indirectly prove yourself to that point instead of having to do the very painful and unintuitive proof that we actually did way back in an earlier section when we actually had to prove that a Fourier transform would allow you to switch bases. And with that, that's the end of 3.6. We can move on finally to the actual problems, and then finally after that to chapter 4.